We'll wait for others to join. All right. So welcome to week 13 of the tutorial fluid mechanics. So I hope everyone is regular to their lecture videos. So the exam is very near soon, and I hope you all have completed your assignments provided by the NPTEL team on the portal, as well as watching the lecture videos by the prof. And those who have missed any of my tutorial lectures, you might have watched on my YouTube channel. You might have got the sheet from the NPTEL where all the links for the lectures corresponding to my name, Varnit Kapoor, are visible in that sheet, as well as the Google Drive link is there for all the PDFs. Those who are joining for the very first time on my YouTube channel, so corresponding to each course, there's a playlist. And in each video description, you will see the link for the Google Drive for the PDF notes. So let us start. Just let me share the screen. Please hold on. I hope my screen is visible. Great. So let us start. So we were discussing the topic related to the shear stress distribution in the circular pipe flow. Okay, that is, we were dealing with the Hagen-Poiseuille scenario. Okay, and we'll start in the continuation of that for the velocity distribution in the laminar pipe flow. So let me write velocity distribution in laminar pipe flow. Okay, so again, we have some assumptions as we did last time. I'll just write once again. So the first one is the flow is steady flow, uniform flow, third is viscous laminar flow, and the flow should be fully developed. Okay, so we have so far calculated the shear stress. From this shear stress, we can get the velocity, actual velocity. Okay, from this actual velocity, we can get the flow rate. Okay, also from the actual velocity, we can get the mean velocity concept. If we know the mean velocities, we can also again get the flow rate. And from the mean velocity, we'll get the concept of losses, okay, head losses. So let me draw the diagram once again. There is a pipe in which the flow is happening. Okay, So I assume that my y direction is from the base, okay, and from the center line it is R, direction r. Let us assume, okay, radius r is the radius of the pipe. Okay, so shear stress distribution, as we have seen, it is a linear distribution. So with increase of r, the shear stress towards the wall increases. We have seen this thing in the last tutorial, that our shear stress distribution somewhat look like this. So it's maximum at the and minimum towards this. Okay. We also need to have a velocity distribution. So let us get the velocity distribution. So shear stress profile relation was tau is equal to minus dou p by dou x into r by 2, where r is measured from the center line. Okay. This is your first equation. Also, shear stress from the Newton law of viscosity for a non-viscous fluid, mu dou u by dou y. Okay. If you compare both of them, and we know that from this geometry that r plus y is your capital R. Okay, radius of the, this r plus y is nothing but your capital radius r of the pipe. So what will be dr? Dr plus dy will be 0 because capital R is constant. So dy is nothing but your minus of dr. Okay, minus of dr. So if you compare both of them, the above two, so minus dou p by dou x into r by 2 is equal to mu dou u by dou y, mu dou u by dou y. So from here, what will be the velocity du if we come to the 1 by 2 mu minus dou p by dou x into dy. So this is basically the, not a partial equation, it's a definite. Okay. So from here we got the velocity du. Now we will integrate it. We know that dy is nothing but your, here if you put this dy, what it will be, your relation will be du is equal to 1 by 2 mu minus dou p by dou x. Dy is r dr with a negative. So this becomes positive, negative and negative, correct? And we'll integrate it. We'll integrate it. So we can take out dou p by dou x outside. Only the integration will be on the r, as 1 by 2 mu is also a constant. So if you integrate it, your du will become total velocity u 1 by 2 mu dou p by dou x r square by 2 plus some constant c. Okay. So this relation is only for fully developed laminar flow, as we have used tau is equal to Newton law of viscosity mu du by dy to derive it. Okay, always remember. So what we can see from here, what we can see is that your velocity is proportional to r square. Your velocity is proportional to r square. So that means y is equal to r square, a parabolic relation it should come. So it should be somewhat like a parabolic relation. Let's say somewhat like a y is equal to minus r square. Okay, if I say, let us keep this as negative only, this negative, so it is minus of r square. So basically it's a parabolic relation. So if you make the velocity profile in here, so your velocity profile will look like a parabolic. So that's what I have been making the velocity profile in my previous tutorials like this, that my relation will be a parabolic relation when the flow is happening inside a pipe. Okay, flow is happening inside a pipe. Now we will apply a boundary condition to get this constant value. To get the constant value, so we know that apply boundary condition. What will be the boundary condition? That at r is equal to capital R, your velocity will be 0 because no slip comes here. So put this value in the above relation. U is equal to minus 1 by 2 mu minus dou p by dou x into r square by 2 plus c. And this is nothing but equal to 0. Your velocity is 0. I can write like this. U is equal to 0 is equal to minus 1 by 2 mu. So if you take it on the left hand side and transpose, is it 1 by 2 mu? So it is 1 by 4 mu, 2 and 2 here, 2 and 2. So I'll write this 2 and 2 as 1 by 4. Okay. Right. So from here we get the constant value as 1 by 4 mu minus dou p by dou x into capital R square. Put this constant in the above relation. So you'll get your velocity profile distribution as U is equal to 1 by 4 mu minus dou p by dou x into small r square minus capital R square with a negative minus outside. So it becomes positive. So it will be capital R square minus small r square. So this is your final velocity profile distribution. Okay. And this is your local velocity. Okay. Local velocity. We know that at center line, the velocity will be maximum. So at r is equal to 0, your u is nothing but your u max. So what will be the maximum velocity? So u max will be 1, put this value above in the above red box relation, minus dou p by dou x into r square. Into r square. Okay, this is your maximum velocity. Maximum velocity. So therefore, what we can say that if you put this above, we can get the, since we know that u is 1 by 4 mu minus dou p by dou x. If you take out r square from this relation out from this, it will be 1 minus small r square by capital R square. And we know that what is this? This is nothing but your u max. This is nothing but your u max. So u is nothing but u max into 1 minus small r square by capital R square. This is the another way to write the relation. Okay. So this is your velocity profile distribution for a flow happening through a pipe. Now we need to find the mean velocity. Why we came across with the mean velocity? We get the velocity from mean velocity from a discharge. So discharge will always be constant when it's flowing through a uniform pipe. Okay. So from the discharge balance, we are getting the mean velocity concept or the average velocity distribution. So mean velocity is nothing but an assumed concept. We have assumed that flow rate is nothing but area into mean velocity, which will be compared with the area into actual velocity, because area is always same. So area is always same or not, that we will see. Okay. So how we can get that? Let me see. Write the concept of mean velocity or average velocity. Or you can say average velocity. So again, I have a pipe. I'll draw. Okay. So my actual velocity distribution looks like this. Okay. Maximum towards the center and decreasing towards the ends. Mean velocity will be somewhat looking like this. We have taken a mean of this velocity. Okay. So that all the velocities either at center line or anywhere is same. Okay. So this is your bulk velocity distribution or average velocity distribution. So this is nothing but your average velocity, whereas this is your actual velocity distribution. Okay. So what we are saying that Q actual is equal to Q average. That is, our flow rates are same. So by theoretical, Analysis of velocity distribution. We can get the flow rate dq is nothing but velocity into 2 pi r circumference into dr. How? Suppose I draw a pipe side view here. Okay, I take a radius at r, a small element of the radius at r. Okay, like this. So let us suppose this is with r and this thickness is dr. Okay, dr. All right, and it means that the velocity is u overall. That is your actual velocity which is going out through. Okay, that is u. This is your nothing but actual velocity. Okay, and this is a small element through which it is passing. So u is dq is equal to area into velocity. Area is 2 pi r into dr. Okay, and what is your velocity? That is u. So q actual will be 2 pi r u or r dr. Okay, u into r dr. We know what is the expression for u. Okay, this is your actual velocity. What will be your average velocity? Q average is nothing but u mean, which we don't know so far. And what will be the area? Pi into r square, through which flow is happening, because it is your average velocity. Now you will compare both of them. So therefore, Q average is equal to Q actual. So it is u mean into pi r square is equal to 2 pi r u r dr. Okay, 2 pi dr. I am writing 2 pi r. R is inside already. Okay, so it will be from 0 to r. 0 to r. So u mean from here comes out to be pi and pi cancels out. U2 is there. R dr 0 to r by r square. This is your u mean velocity. U mean velocity. Okay. And we know what is our velocity profile distribution for a laminar flow. We have derived this velocity profile distribution so far. This one. Okay. This is our velocity profile distribution. We can put this for the laminar flow. So the relation I have highlighted is valid for both laminar and turbulent, because I'm not provided what is the velocity distribution looking like. So this is for laminar and turbulent. I should write like this. Valid for both laminar and turbulent, because for both the discharge will be same. Either it's a turbulent flow or a laminar flow, it doesn't matter, because continuity needs to be satisfied. Every velocity distribution should satisfy the continuity equation. So u mean concept is only valid for discharge calculation and not for kinetic energy or momentum calculations. Okay, because what is a momentum? Mass into velocity. Okay, so velocity is different. Velocities are not same here. So here discharge are equal, and um is not equal to u. Okay, make sure that is not equal to u, although discharge will always be equal. Okay, so it's just a mathematical hypothesis we are doing. Instead of having a actual velocity distribution, we are converting it to a mean flow and average velocity distribution, which both from the graph also, if you see, they are not looking equal at all, but the discharge will be equal. So discharge is nothing but area into velocity. So either you go by actual velocity or an average velocity, so you will get the same discharge. Okay, but momentum won't be same because momentum or kinetic energy have velocity square or velocity linear term, and velocity itself are not same. Okay, that's why it can't be same. So for laminar flow, we know that what is our velocity profile distribution, and it is fully developed, the above case which you have derived. U is 1 by 4 mu minus dou p by dou x, capital R square minus R square. Put this above. So U mean will come out to be 2 times 0 to R 1 by 4 mu minus dou p by dou x R square minus R square minus R square into R dr. On integration, what you are divided by R square. So from here, you will get the mean velocity through a pipe flow. So U mean will come out to be 1 by 8 mu after solving the integration, which is very important relation, minus dou p by dou x into capital square. This is your relation, very important relation. This is your mean velocity. How you can bifurcate? You can write this 1 by 8 as 1 by 2 into 1 by 4 mu minus dou p by dou x into R square. If you remember, this is nothing but your maximum velocity. 1 by 4 mu minus dou p by dou x, this. 1 by 4 mu minus dou p by dou x R square. So this can be said that, from here we can say that U mean is U maximum by 2. U maximum by 2. Okay. For a fully developed pipe flow. Okay. Laminar. For laminar fully developed pipe. Okay. Now we got the mean velocity. We can directly get the discharge also now. So discharge equation. The discharge is nothing but U mean into pi r square. What is your U mean? 1 by 8 mu. Just now we calculated here. 1 by 8 mu minus dou p by dou x into R square minus dou p by dou x into R square into pi r square. So it will be pi by 8 mu minus dou p by dou x into capital R to the power of 4. Since we know that R is d by 2, in terms of diameter, if I want to write, your discharge will be pi by 128 mu. Very important relation. You might have seen this a lot of time. D to the power of 4, and this is nothing but your Hagen-Poiseuille equation. This is your Hagen-Poiseuille equation. In Poiseuille equation. Hagen-Poiseuille equation. Very important equation. Okay. Any doubts still here? This is your final discharge equation. So suppose I have a pipe. Okay. And I am assuming the mean flow is happening. So here mean flow is happening. And pressure head here is P1, let us suppose. Similarly, here it also happening. And pressure head here is P2. Okay. So between them, the length is L. Okay. That is, this is your X1 till here. And this is your X2. Okay. Between 2 points. So your velocity is nothing but your U mean. Okay. So what will be it equal to 1 by 8 mu minus dou p by dou x. What will be dou p by dou x? Minus of p2 minus p1 upon x2 minus x1. That is pressure gradient into r square into r square. So from here, what will you get? The pressure difference P1 minus P2 will be 8 mu VL by R square. And if I want in terms of diameter, it will be, and at divide by specific weight. So P1 by W minus P2 by W, it will be 32 mu VL by WD square. Both sides by W are divided. And R converted in terms of diameter. And if there is inclination also between the pipe, first position is at Z1 height, second at Z2 height. So your piezometric height difference will be somewhat like P1 by W plus Z1 minus P2 by W plus Z2 is your 32 mu VL by WD square. Very important relation you might have observed. Okay, very important. So laminar horizontal, for the horizontal inclined plane, you have to replace by Z. So here P1 by WZ, this piezometric head difference, we have seen that from the Bernoulli relation also, it is equal to your head loss. It is also equal to your head loss. By Bernoulli equation, since by Bernoulli's equation, we have seen that P1 by W plus Z1 minus P2 by W plus Z2, it was nothing but your head loss. Okay. So this head loss can be written in terms of friction factor and friction coefficient. So from friction factor, you can write it as FLV square by 2GD. And from friction coefficient, you can write, since F is 4F dash, so 4F dash LV square by 2GD. So that means our HF can be defined for laminar and turbulent scenario. Laminar, general scenario, laminar or turbulent, or only for laminar. So for laminar scenario, if you compare both the above, this and this equation, your HF will be 32 mu VL by WD square. From the right hand side, HF is 32 mu VL only for pipe flow. Okay, laminar pipe flow scenario. Okay, fully developed. And for general scenario, laminar or turbulent, and this relation is your Darcy's relation. Darcy's relation, which is HF is FLV square by 2GD. So if I want to compare for the laminar scenario, both of them, because both of them for laminar, both of above will be equal. That is 32 mu VL by WD square is FLV square by 2GD. So from here, your friction factor will come out to be 64 by rho Vd by mu. And what is rho Vd by mu? Reynolds number. 64 by Reynolds number. 64 by Reynolds number. And we know that since friction factor is 4 times friction coefficient, so from here F dash will come out to be F by 4, that is 64 by 4 is 16 by Reynolds. 16 by Reynolds. This is a friction coefficient value. So now the point might come, for viscous flow, Bernoulli equation is not valid. That's why we incorporated these, all the Newton's Navier-Stokes equation, where Huygens-Poiseuille, Huygens-Plane-Poiseuille, and cold flow will come out. So for a Huygens-Poiseuille case, we are trying to derive an analogy. We assume that our velocity here, this velocity is a mean velocity, and we incorporated the loss to compensate the viscous effects. Okay, so this velocity is mean velocity. Okay, so then only we have converted our viscous flow into a non-viscous flow scenario because of the mean velocity concept. That's why it's very important for the mean velocity to incorporate the concept of mean velocity so that we can use the Bernoulli equation in this manner and we get our head losses. And from there, we can derive our friction factor and friction coefficient. Okay. Is it clear? So also, we know that since F dash is tau, skin friction coefficient is nothing but tau wall by half rho V square. V is mean V. Okay. And this is nothing but 16 by Reynolds number. That is your rho Vd by mu from above. Rho Vd by mu. So if you compare, your wall shear stress will come out to be 8 mu Vd, 8 mu V by D, sorry. 8 mu V by. So examiner is asking what is the wall shear stress relation for a laminar pipe fully developed flow? Your answer will be this. And another way we can also derive like this thing. We can derive this in some another way also. I'll tell you how. The other sense is like this. As we know that our tau wall expression was minus dou P by dou X into R by 2 for the wall, R by 2, right? And we know that U mean was nothing but 1 by 8 mu minus dou P by dou X into R square. So you divide both of them, tau wall by U mean is nothing but dou P by dou X cancelled out, R cancels out. It will be 4 mu by R. Or you can say R is D by 2, 8 mu by D. So again, tau wall is 8 mu G by D. This is also same. This is the another way of representation, or okay, another way of deriving the relation if not going through a friction factor concept. All right, now let's come to the plane Poiseuille, that is for the plates. Then the cold flow. I'll just take a short break and then I'll be back. Okay, let's come back to the concept of plane Poiseuille, that is for the plates. Plane Poiseuille, that is for plates. Okay, so what do I mean by this is that I have two parallel plates like this, through which fluid is flowing. So fluid is flowing with the free stream velocity, that is u infinity. And from the side view, if I see my plate, it looks like this. So this is your height h between them. And we assume that it's of unit width. That means end effect is neglected. End effect neglected. That means there is no water leakage from the parallel sides of the plate. Okay, so two plates are like this. So from here, there is no water leakage, only the flow is happening like this. Okay. So again, I'll draw fully developed profile. Again, it will be a parabolic relation. I'll just write the relations. No need to derive them. You can see the standard textbooks for that. Okay. So this is my center line. My velocity profile distribution somewhat look like this. Okay. So my y is from y direction is from the center line. Okay. Y direction is from the center line. And this is my velocity profile distribution u. This is h by 2, half of the height between the plates. Okay. Pressure gradient here is dou p by dou x minus dou p by dou x. So my relation will somewhat look like u, similar relation. U is equal to 1 by 2 mu instead of 1 by 4 mu. Again, minus dou p by dou x into, instead of r, it will be h by 2. Okay, from the analogy. H by 2 square minus y square. So if at y is equal to 0, the velocity will be maximum. U is equal to u max. So your u max will come out to be 1 by 2 mu minus dou p by dou x into h by 2 whole square. This is a maximum velocity. And your mean velocity is nothing but 2 by 3 of u max. So what is your u max? It will be 1 by 3 mu minus dou p by dou x into h by 2 whole square. Mean velocity. Okay, these are the expression for all of them. And what will be your discharge? If I want to get the discharge, the value of discharge is Q is U mean into area. So your U mean is 1 by 3 mu minus dou p by dou x into h by 2 whole square. And area is, this is your area through which the flow is happening, h into 1. That is h into 1. Okay. What will be your HF? HF relation is 12 mu VL by WH square, and wall stress is nothing but 6 mu V by H. Similar kind of relations will come up. Okay. 6 mu V by H. Again, for average velocity, the profile will somewhat look like this. Like this. Okay. Okay. But if in the examiner has said that y is the distance from the plate, not from the center line. Here we have taken the y distance is from the center. Then our relations will be different. I'll tell you how. Let me write here. if distance y is measured from the wall, then what will you do? So I'll again draw the this is my central line. Y is from the base. Okay, and I know that this is my h by 2. Again, my velocity profile distribution will be same, parabolic. Okay, my whole length is h. Okay, velocity profile distribution is u. So now, as we know that u is nothing but, if this is y, so this let us suppose is x. Let us suppose this must be x. So u from the center, we assume that it is x. So it will be 1 by 2 mu. We know that the relation is dou p by dou x into h by 2 whole square minus x square this time. Since we know that x is nothing but h by 2 minus y from this. X is h by 2 minus y. So put that x above. So u will be 1 by 2 mu minus dou p by dou x h by 2 whole square minus h by 2 minus y whole square. So from here, your final relation will come out to be, on solving, minus dou p by dou x hy minus y square, hy minus y square. Okay, clear? Now you can get the u mean and all that from the same above relations. Okay, now this was your which relation? Plane Poiseuille flow between the parallel plates. The other case is coet flow. Coet flow, where you have relative motion between the plates. So let us say if the base plate is fixed, above plate is moving because of the velocity of the fluid itself. Okay, so let us say we have fixed base plate and above plate is moving with velocity v of the fluid itself. Okay, and this is again between the plates, so it is h. Okay, this is your center line. But here above part is moving with some velocity. So if you observe, your velocity profile distribution will look like somewhat like parabola's maximum is above till here because it has shifted because of the presence of the above part has a velocity. There is a relative velocity between the plate. It's somewhat lined up a parabola, but maximum will be above here, not at the center line, not directly at the center line. So this V, there is some V because lesser V this much because there is a no slip scenario also. Although above plate is moving, but there is no slip as well. So this is V since no slip is also there. That is why it's a bit lesser than the U maximum. So this plate is moving because of above plate is moving because of the water or sorry, fluid itself. So here the relation will be nothing but a linear profile assumption. We will assume that Vy by H plus the same relation as above of if we are measuring the y from the base. So this is your y from the base. So if I'm measuring y from the base, this relation will happen. Okay. Plus 1 by 2 mu minus dou p by dou x hy minus, this is the relation of velocity. Okay, this is almost required. So here your fluid is coming through a velocity of mean stream velocity of u infinity, and u infinity is always greater than v. Always remember this, u infinity is greater than the v. Any doubts, Neha? Any doubts? Okay. So as I told previously that mean velocity concept is not for momentum or kinetic energy calculations. Okay. But what if you want to incorporate the mean velocity concept, what we should do? So we should come up with some correction factors which should be multiplied with your mean velocities so as to get the exact momentum and kinetic energy values. Okay, so I'll come up with a scenario of variation of kinetic energy and momentum in flow through circular pipe. So suppose I have a circular pipe. Okay, we know that actual velocity profile distribution somewhat look like this. And my mean velocity profile distribution look like this. Okay. So mean velocity is basically defined for discharge. Mean velocity is defined for discharge analysis. The actual momentum transfer rate and kinetic energy transfer rate are more than calculated by mean velocity because of the presence of the actual velocity distribution. So some correction factor is required in the mean velocity to get the actual momentum and the actual kinetic energy. Okay. And if we say for a laminar profile, the correction factor value will be more compared to a turbulent profile. Okay, because there is a momentum transfer much faster in the turbulent flow compared to the laminar flow. Similarly, the kinetic energy transfer as well. So assume that my radius is measured from the center line, measured from the center. So whatever mass, actual mass flow rate will be same as average. Okay, so my momentum rate in average will be mass flow rate average into V average. Similarly, my momentum, sorry, kinetic energy average will be half mass flow rate average V average whole square. Since mass flow rate are same, they won't change. Similarly, but V average are different when compared to the actual. What will be momentum actual? It will be mass flow rate actual into V actual. Okay, V actual. So let me write here like this. V average, and this is your V actual. Okay, and kinetic energy actual will be half mass flow rate actual V actual square. So these terms, this, and this is same because mass actual and mass average are same, as I've said. These all are same, but what is varying? V average and V actual average. So this and this are varying because velocity is different. So that means my P actual, that is momentum transfer actual, will be greater than momentum transfer average, and kinetic energy actual will be greater than kinetic energy average. So I need to have some correction factor, introduction of correction factor. Introduction of correction factor. So for a momentum correction factor, or that is defined by beta, is nothing but momentum transfer actual to that of momentum transfer average. Okay. So what is momentum transfer? P is nothing but mass flow rate into velocity. What is mass flow rate? Rho AV into velocity. So that is rho A V square. This is actual. So beta will be rho outside U, if I say, okay, square into dA to that of rho into U mean in square into A. This is your rho U square dA. So rho and rho cancels out. So beta correction factor, momentum correction factor is nothing but U square dA over, sorry, U mean square A. This is your momentum correction factor. Momentum correction factor. Similarly, for velocity, alpha is nothing but kinetic energy actual to that of kinetic energy average. So it is, since we know that kinetic energy is what value? Kinetic energy is half mass flow rate into V square. That is half rho A V square into V square is V cube. V square into V is V cube. So alpha will be half rho U cube dA upon half rho area, sorry, U cube, U mean cube by. So this and this cancels out. And finally, alpha will come out to be U cube dA only by, if you see, only a difference of order of the velocity. This is A. This is kinetic energy correction factor. So whatever correction you want to give in the kinetic energy, the vector will be alpha, and for momentum transfer it will be, okay. And also make sure, see that since alpha is one order higher compared to beta, so both are greater than one always, but alpha is much greater than beta, okay, as alpha is one order U cube and this is U square. Okay, is it clear? Any doubts? So if I say I give you a profile like this, so I have three different profiles. One is suppose like this. This is your U actual is equal to U average. So both average and this are same. Okay, here U actual and U average are same. Other scenario is that your U actual somewhat look like this, but U average will be looking like this. Okay, the first case is this. Second case is this, where this is your U actual and this is your U average. The third case is your actual velocity profile distribution somewhat look like this. And your again average velocity distribution will somewhat look like this. And this is your third scenario. So you tell me, if I want to apply momentum correction factor, which will be having a higher momentum correction factor. Which case? Obviously, there is a much deviation in the third case of average and actual. There is a huge deviation between them. This is the deviation. So here the correction required is more compared to the second case and first case. Both are same. So we can say that beta in 1 is less than beta in 2 is less than beta in 3. So maximum correction fraction is required in third case compared to the first case. So variation between U mean and U actual goes on increasing from 1 to 3. Since variation in U average and U actual goes on increasing from 1 to 3. Okay. Also, as I said, that correction factor in laminar flow is higher compared to a turbulent flow. So suppose I have a scenario like I have a pipe again. My velocity profile for a laminar flow is like this. Whereas for a turbulent flow, it's more of like this. Okay, so this is turbulent, U turbulent, actual. This is U laminar, actual. If I see U average, laminar, and similarly if I draw U average, turbulent. Okay, so you see that deviation here is higher compared to deviation here, right? Deviation here is higher compared to this. So we can say that correction factor, because of, if you derive the velocity profile distribution also, the relation you can see, I'll write the, as well as there is a more momentum transfer in the turbulent flow because of the presence of eddies compared to a laminar flow. So correction factor in laminar should be than in turbulent, as variation between flows from mean velocity in laminar is greater than in turbulent. Okay, this is your variation. Okay, variations are. Any doubts? So you have velocity profile distribution in laminar case and in turbulent case. So in laminar, U by U max, if I do, it is 1 minus small r square by capital R square, whereas U by U max in turbulent is 1 minus r by capital R to the power of 1 by 7. So here, U mean or U average, I can also say, U average is 0.5 times of Umax. But here U average is 0.82 because variation is less. So it's more near the Umax. Okay, in turbulent case. So momentum correction factor is required for the impulse momentum equation which we derived in the last tutorial. Okay, so whereas the kinetic energy term comes in the Bernoulli equation. Okay, so how I can write for the momentum equation? I can write net force is nothing but correction factor multiplied with P final minus P initial. That is nothing but your momentum correction factor beta into rho QV final minus rho QV initial and here U is mean velocity or V is mean velocity. When you are multiplying the mean velocity, when you are taking the correction factor, then you take the mean velocity. If you are doing the actual, you're taking the actual velocity, then there is no need to take the mean velocity. Okay. So, and similarly, in Bernoulli equation, if I say actual Bernoulli equation, or not, let us not say the energy equation, we can say. So suppose I have a pipe like this. So at this section, I know that velocity profile is, actual velocity profile is this, mean velocity profile is this. Okay. So there is a loss eventually. So therefore, your equation will be P1 by W plus alpha square V1 square by 2G, V1 square by 2G plus Z1 is equal to P2 by W plus alpha square, alpha 2, alpha 1, V2 square by 2G plus Z2 plus losses. So there is an alpha here. Okay, because of the presence of loss. This is your first position. Similarly, your second section also. Your second position. Okay, and these are your mean velocities. Always remember. These are your mean velocities. Okay, any doubts? So let me write the values of beta and alpha also. So my beta value for a laminar case and a turbulent case is 1.33 for laminar and 1.03 for turbulent. Okay, that means your U by Umax relation is, I have already derived, no need. The turbulent relation here. Okay, and alpha for laminar and turbulent so for laminar it is 2 and 1.33 for turbulent. Eventually, correction required in turbulent flow is less than the laminar flow always. Okay. Any doubts till here? So if no doubts, we will start with next topic of flow through pipes. We'll take a short break and then we'll jump. All right, let's be back. Let's come to the concept of flow through pipes. So for the full depth flow in a closed conduit, okay, so it's nothing but a shape. Whatever shape you have, a closed shape is known as a pipe flow. And in pipe flow, different losses occurs. Okay, in pipe flow, different losses occurs. Let me write. Full depth flow in a closed conduit is known as pipe flow. Okay, and in pipe flow, eventually when the flow is happening through a pipe, there will be losses occurring. In pipe flow, different losses occur. We can classify these losses as major losses and minor losses. So losses can be classified as major losses and minor losses. Okay, so what are major losses? When a flow is happening through a pipe or a conduit, these losses are due to the presence of the viscosity of the fluid. So there is a viscous resistance between the layers of the fluid over the entire length in the flow, and their magnitude is very large compared to the minor losses, as well as occurrence is large. Magnitude is also large and they occur very frequently. So far we were dealing with the major losses. Okay, so suppose I have a scenario like this. I have a like pipe like this. So there will be no slip phenomena, viscous resistance will be there. So these losses are due to viscous effect from a line between them. Viscous effect or resistance over entire length in flow okay, the magnitude is large. Sorry, I should resistance I should write till here, and then the magnitude over the entire length in the flow is large, as well as the occurrence of, it happens very frequently, occurrence is large. Okay, occurrence is also large. Whereas the minor losses are due to the change in the momentum of the fluid. Suppose the direction is changed or sudden expansion or contraction is happening. Okay, so the magnitude is less and occurrence is less also. So that is all why they are also known as variable velocity losses. All right. So suppose I have a scenario like this. Again, same kind of scenario. So here, if you see sudden compression, sudden expansion, okay, there is a loss. So there is H entrance, H at exit, okay, or expansion you can say. Or suppose you have a bend in the pipe, okay, so there is a velocity change, momentum change, transfer. Or if there is a, you say a valve is there, then there will be a loss, valve, because of the presence of that valve. So these are due to change in momentum of the fluid, that is due to change in the velocity, magnitude of the velocity or the direction or both, okay, because mass flow rate is constant. Their magnitude is less, and occurrence is less, also less. So they are known as variable velocity loss. Okay. So examples, some of the examples are like sudden expansion or contraction, or entrance or exit loss, bend in the pipe, or if you have pipe fittings like walls. Okay. So we have seen all the major losses so far. I'll write the expressions for all of them again. So there is one way is the Darcy-Weisbach equation, or other way is a Chassis equation. Major losses. One is Darcy's Weisbach equation, and the other is Chassis. So this analysis is done based on the assumption that flow rate is constant. Okay. So Darcy's Weisbach equation can be used for scenarios like steady flow, second is uniform flow, or if you are assuming mean velocities. Okay. So you have seen that Hagen-Poiseuille relation where we have just derived FLV square by 2GD or 4F dash FLV square by 2GD. Okay. So that D is your characteristic length. Okay. So if it's a pipe, your characteristic length will be the diameter of the pipe. If it's a square shape, so or any other shape, it will be 4 times area by the perimeter. Okay. It depends on that. So we have seen the relations. So for all the pipe flow relations, we have seen that H was nothing but FLV square by 2G DH. DH is nothing but your characteristic length. Okay. Characteristic. This is your characteristic length, and capital length is nothing but your flow of the length. Okay. So if we have a pipe for circular pipe, d of h is nothing but your diameter. So h will be nothing but hf, we say. Hf is nothing but fl, and also we know that v is nothing, q is equal to av, so q will be pi by 4 t square. So if you put an above relation, hf will be what? fl q square by 12.1 d to the power of 5. Okay, always remember. And f is 64 by re for laminar flow, the laminar scenario. But this relation is valid for both laminar and turbulent. Okay. Whereas if I have a steady flow scenario, the Chassis-Weisbach equation is there, and this is suitable for the open flow measurement devices, basically. Okay, like you have a piezometer, manometer. So sorry, piezometer you have, it's an open flow device, right? Or a pitted tube is there. So it is basically used in steady flow scenarios. Here, if suppose you have like this pipe flow, which is suppose at position 1 has okay. So there is a flow rate happening at this position as well as this position. Velocities are same. This is at Z1. This is at Z2. But some loss has occurred in the meanwhile. Okay. That is pressure head has lost. So pressure head is lost from this level to this level. So let us suppose that the inclination angle is I between them. So there is a head loss. So there is a head loss. HF, piezometric head loss. Head loss. Okay, there's a piezometric head loss. So here it was P1 by W till here. And here it is P2 by W. Okay, and this length supposes length not this. This length between them is L. Okay, so my velocity V is nothing but C times M into I, where C is my Chassis coefficient. Okay, M is the hydraulic mean depth. Again, some characteristic length kind of scenario, which is A of the cross section by the perimeter P. Okay, and I is your slope. That is HF by L. HF by L. This was not the angle, sorry. Perpendicular by base is your I. Okay, so tan I is nothing but or small in change HF by L. I is tan I or I is HF by L, whatever you can write. Okay, so from here you get the loss HF. has happened between them. Okay. I'll use line to distribute the okay, great. So I've written the relations for the losses of major cell. Now I'll write a relation between shear stress at the wall and friction factor. Factor that was F. Okay. So we know that friction coefficient is nothing but tau W by half rho V square, and F is friction factor is 4 times of friction coefficient. So that is 4 times of tau W by half rho V square. Therefore, from here, what will be your wall stress? F by 8 rho V square. So if you say tau W by rho under root is under root of F by 8 V. Okay, this V is in meter per second, and this F by 8, this term is also a velocity only. So this is shear or friction velocity. This is your unit is of a meter per second, so it is V star. It is under root of F by 8 into mean velocity. So this is your mean velocity. And this is your shear or friction velocity. Okay, because both have same units will come out. If you do tau W by rho by dimensionless, it will be meter per second. Okay. Now we come to the concept of hydrodynamically smooth and rough surfaces for both laminar and turbulent flows. So as I have said in my turbulent flow transition zone, there is a laminar sublayer thickness is there. Okay. So if we say for a laminar flow, it is independent of whatever the surface roughness is of the surface. So if surface have what very rough, little rough, it doesn't matter. Laminar flow will always be independent of the surface roughness. Whereas the turbulent flow depends on the roughness of the surface, that it is smoother surface or a rough surface. Let us write this. Hydrodynamically, smooth and rough surface. So laminar flow is independent of surface roughness. Why? Let us see. So suppose I have a plate like this. It has some roughness. Assume that it has some roughness over it. Making some small roughness to show this over the blade. Okay, some small grooves are there, and the flow is coming with the mean stream velocity. Okay, the flow has an inertia effect through which it is coming through a velocity. So the flow will mostly will be remaining laminar, although here there will be a no slip condition happening. So, but the flow will be having most of the inertia and will be moving in some parallel layers once it is fully developed. Okay, so that is why it will go on in the parallel layers very smoothly over the any kind of surface, either it is rough or smooth surface. Okay, since as inertia effect of U infinity is more, this implies flow remains laminar. Okay. Whereas when we come to the turbulent flow depends on the surface roughness and smoothness. Okay. Suppose if I have a scenario of a smooth surface. So smooth surface means very small grooves are there. And there is a laminar sublayer thickness which happens during the transition from laminar to turbulent. So suppose that my laminar sublayer thickness will be, in such scenarios, will be delta dash. And this is your thickness of your roughness. That is your K. Okay. So this is average height of your roughness. But here, your laminar sublayer thickness is delta dash for the smooth scenarios. Smooth. So that means this is K is your average height of roughness. So that means your delta dash is greater than K. What was your expression? So what will be K by delta dash? Is nothing but less than 1, and it is near around less than 0.25 only. Okay. We know that what is the expression for delta dash? It was 11.6 nu by tau w by rho. Tau w by rho is nothing but your V star. Just now we derived this. Tau w by rho is your V star, under root of tau w is less than 0.25. So from here we can get the V star times K by nu is less than 3 for a smooth surface in case of a turbulent flow. So it's nothing but Vd by nu is your Reynolds number, V into some K by nu is your relation for defining a smoother. You can have an analogy to remember. Okay, from instead of the characteristic length in the Reynolds number, it is K this time. That is your average height of the roughness. Okay. I know it's pretty much sometimes difficult, but if you see once again, all these relations will make sense to you and will be very easy. But whereas if I have a scenario like this, I have a plate where my surface roughness is of much higher length compared to my laminar sublayer thickness. So suppose my surface roughness is like this. So this is my thickness of surface roughness, whereas my laminar sublayer thickness is delta dash. So here, rough surface, here my delta dash is less than K. Previously, delta dash was greater than K. So what will be K by delta dash for this? It is greater than 6. Okay, this is your condition. So we can say that what is delta dash? 11.6 nu by V star is greater than 6. So from here, your relation will come out to be V star times K by nu is greater than 70. Okay, is greater than 70. So K by delta dash varies from 0.25 to 6. You can see. Okay. Now the question arises, how will you measure your friction factors? We are just saying that these are your friction factors, but how you will measure? Measurement of friction factor, that is F. F is your friction factor, right? So there is two ways. One is you use a mathematical correlation. Other is you can use some chart that is known as standard Moody chart. Okay. So one is using your correlations. Which have been derived in the literature, as well as the other is Stanton Moody's chart. Okay. So let us go first for correlations. So there is a friction factor F. So it will be defined both for laminar and turbulent. Laminar and turbulent. So we know that we have just derived that the laminar scenario is when RE Reynolds number is for a pipe flow is less than 2300, suppose. Okay. So F is 64 by Reynolds number. Okay. Whereas when Reynolds number is greater than 4000, the flow is turbulent for a pipe flow. And again, it will be the friction factor will be defined for a smooth as well as rough pipe, because in turbulent flow depends on the roughness of the surface, that is your pipe here. So here for smooth case and for your rough case. So in case of smooth pipe, let me write. So in smooth pipe, where your Reynolds number is less than 10 to the power 5 and greater than 4000. These are smooth scenarios. So here your friction factor is 0.316 Re to the power of 1 by 4. These are the relations you have to, no need to just you have to remember them. Okay. For a rough pipe, your friction factor scenario is 1 by under root of F is nothing but 1.74 plus 2 log on the base 10 R by K, where R is your pipe radius. Okay. Pipe radius. Okay. Whereas you will see some smooth Stanton Moody's chart. So I won't discuss that here, but I'll just tell that how it looks like. So it somewhat look like this. So you have a chart like this. You have a laminar regime. You have a Reynolds number scenario regime. Up till here, suppose I have RE less than 2000, 2300 or whatever. And here it is RE greater than 4000. Okay. So the friction factors values are here on the y-axis, and this tells us the transition zone. So this some values will come out here, and for this up till here it is smooth. Above that, suppose here it is near around a rough scenario, rough pipe. Okay, and there is a concept of relative roughness, and this roughness doesn't depend. If you see here in the rough pipe, it doesn't depend over the Reynolds number. It is not a function of Reynolds number. Instead, it is a function of the relative roughness height. Okay, that is K. Whereas in here and in this laminar and turbulent smooth pipe, it is dependent on the Reynolds number, not the K value. Okay, and there is a you get a value of epsilon, that is K by D, where epsilon is relative roughness. Okay. Okay, relative roughness. So somewhat like this, a Moody chart look like. I just want to give a scenario. And there is one relation I want to make a note of here is that no need to derive it. Just I'm saying that for a turbulent pipe flow, your U over U max over U mean or U average is nothing but 1 plus 1.33 under root of, very important relation. Okay. Clear? Any doubts? So F depends now on, it's a smooth pipe, turbulent pipe flow, smooth, or this F depends on smooth or rough. You will use the relation from here accordingly. Okay. Now let's come to the write down the minor losses as well. Minor losses. Just hold on, I'll be back in a minute. Okay, minor losses. So the relation for minor losses is nothing but K is minus, this is not roughness, some coefficient K times B square by 2G. Now this K changes for different scenarios. So scenario one, number one, if my scenario is sudden expansion, that means I have a scenario like this. Suddenly my fluid which was coming expanded. Okay. So my H experimental value is V1 minus V2. So this is a position 1. This is a position 2. V1 minus V2 by whole square by 2G. Okay. Or also you can write K experiment if you have V1 square by 2G. All right. This is your relation. Second is exit loss. Or let us write sudden contraction. So when there is sudden contraction means, oh, so this was expansion. Flow from here came to here, 1 to 2. So here, when contraction is happening, again, you know that there is a vena contracta. We have discussed this. C scenario. So H contraction will be, that was H expansion. This is not K expansion. So no, it was not experiment. Sorry, it was expansion. H contraction will be Vc minus V2. So this is 2. Okay. Whole square by 2G. Or V2 square by 2G into 1 by Cc minus 1. You know, Cc is coefficient of contraction. We have discussed this. So this is your H contraction. And if this relation is not given, this can be also taken as 0.5 if not given. If Cc not given, sorry. So you will assume this whole term to be 0.5. Next is your entrance loss. So entrance loss means, suppose you have a scenario like this. Okay, so again, fluid came, contracted, and expanded. Okay, entered in some of the section. So H entrance is nothing but 0.5 V square by 2G. Okay, or if there is a K, it's given K as an entrance, K entrance is given to you. That will work. This is your K entrance. Okay. Next is your exit loss. One is entrance loss. Next is your exit loss. So scenario is like this. Now it is exiting in some ambient. So here V will be 0 in area. This area is infinity. This can be like ambient, it is exiting out. So velocity V1 is there, but V is 0. V2 is 0. Okay. So it will be H exit V square by 2G. Okay. Then we have a bend loss. Okay. Bend loss. So why there will be a bend loss? Let us understand one thing. Suppose the pipe is bent. Okay. So there is a contraction which is happening. So initially the fluid was flowing like this. Should make like this. So initially fluid came like this. So it wanted to travel straight, but because of the bend, it has to move. Okay. So there will be a redistribution of pressure and velocity from inside. Okay. Because of the pipe bend and the spacing between these streamlines which are there. Okay. Because of that, there is a high pressure zone has been developed. Okay. And they increase the pressure. So the spacing between the streamlines will increase towards the outside wall and decrease towards the inside of the bend. Because of that, there will be a pressure jump. Okay. P will increase here. Okay. So high pressure zone. This is a scenario of a high pressure zone. Because most of the fluid started accumulating here because of the presence of the bend. Okay. So here your H of bend is nothing but K into V square by 2G. K of bend into V square by 2G. So as the bend increases, if the bend is exactly like 90 degree, so K has increased very far. R has decreased and K is increased. So in this scenario, R decreases, K increases. This implies H of bend increases. Okay. Next is your sixth, that is valve loss. So I'll make a short graph here is that with radius of curvature ROC, your K of the bend, if the radius of curvature increases, so if you see radius of curvature is less, so K was high. Similarly, it will somewhat graph will look like this. If it is been asked by the exam. So suppose I have a valve connected the two pipes. So again, H valve will be K of valve V square by H. Okay, these are your minor losses. All right. Now let's come to a compound pipe scenarios where we have a pipes in series and parallel. Pipes in series and parallel. Compound pipe. First is series connection. So series means your flow rate is same always. Okay. So suppose I have a scenario like this. Pipes are connected like this. Okay. So here, whatever the flow rate is, here the flow rate will be same, and here also flow rate will be same. So if we assume that minor losses are neglected, so it's same like a circuit, resistance circuit, voltage battery system kind of scenario where the current is same in series and in parallel it is distributed. Similarly, here the flow rate is same in the series and in parallel it will be distributed. So if we say that if minor losses are neglected, so how we will add up the losses altogether, the major losses. So my H equivalent for this whole pipe HF equivalent. So each section has HF1, head loss in pipe 2, head loss in pipe 3, and so on. So it will be sum of all the head losses and so on. Okay. And we know that for a pipe, circular pipe, it is the relation we have just derived, just written above, that is FLQ square by this relation, 12.1 d to the power of 5. So the only variable term is length of the pipe, flow rate is same, friction factor is same for the material of the pipe. 12.1 is a constant value. Only different values are, and flow rate is same. So only L and d to the power 5 is the changing variable. So for a pipe flow, it will be L equivalent by D equivalent for circular pipe. I'll write here. Is equal to L1 to the power D1 to the power of 5, L2 upon D to the power of 5, and so on. So in series, flow rate is same and losses are added up. It's similar like a current and the potential. Potentials are adding up. Whereas in parallel connection, flow rates get distributed and losses are equal. So I'll write here parallel scenarios. So it's a scenario like suppose I have like this. My flow rate was Q here and it got distributed in Q1, Q2. Suppose my head loss in this pipe was HF1 and HF2 in this. Okay, that means my Q is Q1 plus Q2, whereas my potential that was V1 minus V2 and V1 minus V2 will be same. That is equivalent head losses, whereas HF1 is equal to HF2 is equal to, and so on. Here my potentials are same, whereas my flow rate is Q1 plus Q2 and so on. So I can write, since for circular pipe, HF is FLQ square upon 12.1 d to the power of 5. So HF is same in all of them. Friction factor for a material is same of a pipe. 12 is a constant value. L is changing, D is changing. So Q can be written as d to the power 5 of L. Okay. So from here, Q is proportional to d to the power of 5 by 2, 1 by 2, because it is Q square. So therefore, D equivalent to the power of 5 by 2 upon L equivalent to the power of 1 by 2 is equal to d1 power 5 by 2 L1 power 1 by 2 plus d2 power 5 by 2 L2 power 1 by 2 and so on. Okay. So it's a scenario somewhat like this. If I remove this complete diagram, this was to explain only. So my scenario of the pipe will be like this now. So this is like Q. This is Q1, Q2, Q3. Okay. Passing through the pipes. Okay. Is it clear? I'll just brief a concept of total energy line and hydraulic energy line. Total energy line, that is TEL, and hydraulic energy line, that is HEL. So total energy line tells about the total head of the flow basically. So TEL is nothing but P by W plus datum head, pressure head plus datum head plus dynamic head. Whereas hydraulic energy lines only tells about the piezometric head in the flow, that is P by W plus Z. So difference of total energy line minus hydraulic energy line is nothing but V square by G, V square by. So that means therefore total energy line is always greater than hydraulic or equivalent to hydraulic energy line. If the fluid is at rest, then both will be same. Okay, so in fluid flow, total energy line is always greater than hydraulic energy, and both can coincide at a stagnation point when the velocity is zero. So if there is a pressure in the pipeline greater than the atmospheric pressure, hydraulic energy line will be always be above the pipeline only. Okay, and in the fluid flow of momentum, then the momentum of the flow reduces as it expand in the case of diffusers, and dynamics of the flow is converted into the piezometric head. Okay, always remember that thing. So hydraulic energy line tells us about the locus of the flow, how the flow is having a, what kind of locus is there of the flow. So suppose if I draw a figure like this beaker, two reservoirs are there. Okay, one beaker is here. Suppose this is from the base. There is a level here, there is a water level here. This is maintained at Z1. This is maintained at Z2. Okay, so from here the flow happens from position A to position B. Okay, there are some piezometers which are being attached here while going downstream. Okay, eventually the pressure will be lost because of the presence of loss, roughness, smoothness, or whatever, the major or minor losses. So basically, so these are your fluid, the piezometric head level. So this is basically your line joining is your hydraulic energy line. That tells your piezometric head. Okay, from that point. Suppose this is your point at position Z. So this is Z and this is P by W. So P by W plus Z is your piezometric head. So that tells you hydraulic energy line. Whereas what will be your, because of the some entrance minor loss present here, there is a dynamics of the fluid v square by 2g, and there is some again loss here. So this tells you about the, I'll write once again, this is your total energy line. This is your hydraulic energy line. Okay, so if I, how the total energy lines come? If I put a pitted tube inside this, suppose. So again, there will be, if I see from here to here, there will be v square by 2g because of the stagnation. This is a pitted tube. Okay, these are your piezometers, pitted tube, and these are your piezometer. Okay, so it's always that energy line, total energy line is always above the hydraulic energy. I think this much is enough for understanding. All right, so here we finish up with the NPTEL, all the week 13 weeks of lecture. I expect that if some topics of the boundary layer is left, I might do on myself, not from the NPTEL side. So if you want to join, you can join. I'll record the session and put it on the YouTube, my YouTube channel. If you want to join, the link will always be remaining same. Those who have enrolled in the course, I'll keep the link to be same. So if from my end, the course ends here from the NPTEL side. And I wish you all the best, everyone, for your exam, which is going to be conducted soon. I hope everyone do well. Those who have missed any of the tutorial, they can watch directly from the links which are provided by the NPTEL team, the sheet corresponding to my name, Varnit Kapoor. All the links are there for each video, and the Google Drive link for the PDFs is there. Those who are new, watching through my YouTube, directly from the YouTube, my YouTube channel name is, I'll write here, NPTEL with Varnit. This is my YouTube channel link. You can directly see for every course. So I have taught fluid mechanics, thermodynamics in the last past 1 year. And for there is a playlist for each of them. You can see, check out the playlist for each of them. And in each video description, you will see a Google Drive link corresponding to that course. All the PDF notes are there for in the Google Drive. So thank you very much for giving me the opportunity to teach you all to this course. And I'll hopefully see you soon in any of the upcoming course in the coming semester. Thank you. Take care. Bye-bye.